Hi, I am Görkay Aydemir from Koç University, Istanbul, and I am going to present our paper Adapt, Efficient Multi-Agent Trajectory Prediction with Adaptation. In this paper, we address the problem of trajectory forecasting for autonomous driving. Our goal is to predict the future locations of agents by considering the map information and the past location of agents. There are two types of objectives in trajectory forecasting: single agent prediction and multi-agent prediction. In single agent prediction, our goal is to predict future locations of a selected agent, called the focal agent. On the other hand, in multi-agent prediction, the goal is to predict future of all agents. Multi-agent prediction is a more realistic approach because we need to consider all vehicles while planning for the future trajectory in autonomous driving. In this work, we focus multi-agent prediction. There are two ways of doing multi-agent prediction depending on the reference: agent-centric and scene-centric. Agent-centric is the natural choice for single-agent prediction. In this reference, all scene elements are normalized with respect to the focal agent, providing a pose invariance. However, to do multi-agent prediction using agent-centric frame, we need to iterate all agents, resulting in a computational complexity linear in the number of agents. On the other hand, in scene-centric approach, all agents are represented in a common global reference frame. This reference frame is more efficient for multi-agent prediction. However, we sacrifice pose invariance. We follow a scene-centric approach for efficiency and propose an adaptation strategy to account for the lack of pose invariance. This shows an overview of our approach Adapt. We first encode the provided map elements and agent histories. We then follow a goal conditioning approach where we first predict a set of possible goal locations, called endpoints, and then learn to interpolate the trajectories leading to these predicted endpoints. Goal conditioning is commonly used in trajectory prediction. Our novelty comes from the adaptive head to adapt to the situation of each agent with the dynamic weight learning. Let's look at each in detail now. Following VectorNet, we use the vectorized input format and form polylines. We encode each polyline with a GNN called subgraph. Then, following LaneGCN, we relate polylines to each other. This way, the agent features become aware of the map and other agents. Given agent features, we predict possible endpoints. There are two modes, single and multi-agent. In single agent case, we predict endpoints for the focal agent using a simple MLP head. In multi-agent case, we use an adaptive head. With the adaptive head, our goal is to adapt to the situation of each agent. Since we are using a scene-centric coordinates frame, we do not have the guarantees of pose invariance. In the adaptive head, we predict the weights that predict the endpoints. This way, weights can be adjusted to represent the viewpoint of each agent. After endpoints are predicted, we refine them by predicting an offset for each endpoint. For independent optimization of different modules, we detach the gradients of endpoints. Then, condition on endpoints, we predict trajectories for each agent using a simple MLP. Similar to the refinement step, we apply gradient stopping to each endpoint. Thanks to our efficient architecture with gradient stopping, we can reach state-of-the-art performance with a very small module size. To better understand where ADAPT stands in terms of efficiency and accuracy, we will show plots using the results reported on Argoverse 1 challenge. This plot represents the number of parameters versus error. Ours is located on the bottom left. This shows that our method achieves one of the lowest errors with a very small model. This one represents the inference time versus error. Again, ADAPT is located on the bottom left, showing that it is one of the fastest and the most accurate methods in trajectory prediction. Here, we present some qualitative examples from our single-agent predictions on Argoverse. On the left, ADAPT can predict trajectories corresponding to different speeds depending on the agents in front. On the right, we see two different behaviors predicted, going straight and turning left. We also visualize multi-agent predictions on the interaction dataset. On the left, we show a turning scenario where the location of agents depend on each other. On the right, we see another complicated scenario. In conclusion, with goal conditioning, we propose a unified trajectory prediction framework that can be used for both single and multi-agent settings with the same backbone. Second, we propose a dynamic head using dynamic weight learning to adapt to situation of each agent in a scene-centric reference frame. And combining all, we propose an efficient and accurate method for trajectory prediction. For more information, you can check our paper or website.